Okay, so once again, anybody who's watching the video, we apologize for kind of coming in the middle. All right. So anyway, if we take a negative 3 and plug it into there, into F, we get negative 6 divided by 0. Now, the reason that makes a vertical asymptote is because it has to do with infinity. All right? And I don't know if you've ever thought of this, but why can't you divide by 0? Besides the fact that it's undefined.
Because you can multiply anything by 0 and get 0, so you can't reverse the operation.
Because there would be no answer because it could be anything, right? And another way of thinking about that. Another way of thinking about that is think about, instead of thinking about 0, think about just really small numbers. If I took 6 divided by, say, 0.1, what is that? 60, right? 6 divided by 0.01. 600. 6 divided by 0.001. 6,000. So as the bottom number here gets smaller and smaller and smaller, the fraction itself gets bigger and bigger and bigger. So theoretically, the smallest number I could divide by would be 0. So therefore, if the smaller it gets in the bottom, the bigger the fraction gets. If you divide by the very smallest number, you should get what? Well, the very biggest number, right? And there is no biggest number. Not infinity, that's not a number. But if you could divide by 0, then you get 0 divided by 0. Now, that's a whole other thing. Divided by 2 is 0, 0 divided by 3 is 0, 0 divided by 4 is 0. So normally 0 on top means when you divide by anything, it's 0. Well, not when you divide by 0. So on the one hand, you've got 0 on top, which makes the fraction go to 0. And you've got 0 on the bottom, which makes the fraction go to infinity. And so you've got these competing things going on. And that's why 0 divided by 0 does not give you a vertical asymptote, because it's not going towards infinity. 6 divided by 0 goes to infinity. 0 divided by 0 does not give you a vertical asymptote, and that's where we usually get a hole in the graph. Okay? So, back to this idea here. So, what's going on in that picture, if we look at it, when we want to talk about the range? So, on Brittany's picture here, Brittany, go ahead and go into trace mode. Okay, go to the menu and trace. And let's trace at 3. And sure enough, just type a 3. Yeah, just type a 3 be the fastest. See there. Okay, look what she gets. She gets 1/6. Okay, well that's on the G graph. You put a 3 in, you get 1/6. Now hit the up arrow. Remember we talked about that the other day? That'll take you to the other graph. She hits the up arrow, 3 is undefined. So right at that point right there, there's a hole in the graph. All right, so now let's do the range. Let's talk about the range question. Let's do the G graph first, the blue one. Well, what's the range? Well, it's y values, right? So you can get all the y values except 0. You can't get 0, and then you get all the positives, right? So the G graph would have a range of everything but 0. So you could say y could not equal 0. We probably ought to say something like g maybe did not equal 0. Or you can go negative infinity to 0, and then 0 to infinity. Something like that. Okay, but what about on the F graph? It can't equal 0, and it can't equal what else? What other y value is not on the red graph? 1/6, where the hole is. That spot where the hole is, there is no y value of 1/6, because these y values over here would all be below 1/6, and these y values on this side would all be above 1/6. So where that hole was would be eliminated. So the range here is everything but 0 and also 1/6, because of where that hole is. So in algebra class, you talked like these two were the same, but really, as functions, they're close, but they're not the same. All right. So that was, I think, most of the issues probably on 49. Then I talked about horizontal asymptote, vertical asymptote. We kind of saw that there. Okay, anything else I didn't cover there? Those are ones I wanted to cover for sure. Nothing? Okay. All right. Let's talk about the quiz tomorrow just a little bit. All right. Now, this is something I'd written up, I think, last year. I've written some stuff on the board here that's very similar to what you see on the screen right there. Okay? So, in section 1.1, we were introduced to the piecewise function idea. I said that you will have to do that on the quiz. You will have to graph. Here's a graph of a piecewise function. Write what that piecewise function is. You know, f of x equals curly bracket, you know, something, something, something with the domain off to the side of it, just like we did on the homework. Review that if you want to. The homework today is trig stuff that isn't on the quiz necessarily. Okay? Now, I was telling your class, that's the homework for tomorrow, but I'm not going to come around and check it. I mean, your first priority is review for the quiz and make sure you're ready for that. After the quiz tomorrow, there'll be an assignment, kind of a shorter assignment for Friday, but if you don't get to all the trig stuff that I assigned today, you can get it done for Friday. That'll be okay. But plus it's Halloween. But, you know, so we'll work in class some today on the trig. We'll go over it and have some work done in class. But, you know, if you want to focus more on reviewing for the quiz tonight, that should be your first priority. So we talked about the piecewise functions and being able to do that. Or maybe here's a piecewise function or a graph, a piecewise definition, and then you write the graph of it. We did one of those in the homework. And to do those are probably made up of lines and possibly a part of a circle. So you make sure you know your point slope form or y was MX supposed to be, however you want to do it. And then your equation of a circle, so you can work with that. Remember, you got to solve that for y in your circle equation. That's when we got into the function notation. We talked about things like domain and range there. Of course, we did a lot of that here in section 3 as well. You know, for example, the function notation. I mean, what's that mean? Well, I remember we had one problem, and a bunch of people struggled with it, and I couldn't quite figure out why. Now, hopefully, we're better off now than we were then. But if I gave you a graph, you know, if I just gave you this graph and I said this was a graph of f, and I said, what's f of 2? Well, I had people coming to me and asking, well, you know, what's f of 2? I don't, there's nothing to plug in. In other words, when you see f of 2, you think, well, you got to plug a 2 in for x. But if there's no equation, what do you plug it into? Well, you can get it off of a graph, too, right? So in this graph, what's f of 2? 3, right? That just means what's the output when you put a 2 in for x, so that would be 3. So, I mean, just that idea of function notation, whether it's a graph or an equation or whatever it is, doesn't matter. Okay, so that's being comfortable with that function notation. When we got into section 2, we talked about shifts and stretches and flips, you know, like we were doing today. You may have to sketch a graph. Here's a graph. Now sketch it, you know, stretched by 2, or sketch it shifted. Or I might just, depending on the time, I might just give you one, like we had today, where you just say what happened. You just say, well, it'll be shifted 4 to the left, and it'll be stretched vertically by 3, and it'll be shifted up 1. You know, that kind of thing. So you just describe it in words. Okay, so be able to do that. Section 2 is when we did that stuff with even, odd, and periodic. We went through some even, odd today. We had talked about folding and symmetry and all that stuff. That's where the calculator could come in too. All right, I might give you just a graph and ask you is it even, odd, or periodic, or I might give you a function that you have to go to your calculator, put in, draw a graph of, set a window, and then is it even, odd, or periodic? I mean, to be honest, if you can graph it, that's the easiest way to tell if something's even, odd, or periodic. So look at that symmetry and look at the repeating. But also be ready to talk about periodic like we did in our homework, you know, a period of 7. You know, so what's f of negative 14? Well, that's 2 periods this way, to the left, right? So it would be the same output. Or f of negative 30 and f of 40, they're 70 apart, 10 periods. You know, be able to talk about periodic using that notation as well. Section 3, we were really talking about these different functions, you know, and we did a lot of domain range kind of issues. And then this last part, so I want you to be able to get a function on your calculator like Brittany just did. Find a maximum. You know, when you get to maximum, a lot of times it just says. You just trace to the peak and it says that you're at the maximum, so that's pretty nice. And I might ask you some of that stuff. Be able to analyze a problem in context. Like we had a problem about the balloon, the altitude, the velocity. I might ask you questions about, hey, this point on the graph, you know, where is the point on the graph where the velocity is the highest, or what's this mean when the balloon's going up? Or, and we had, what else did we have? We had, well, not so much in this section, but in section 2, we had the problem about the child's temperature rising, and how that graph would look. Or we had the volume of the water in the hemisphere bowl, and what that graph looked like. And so just, if you have a problem in context, given units and stuff, to be able to look at a graph and be able to analyze what's happening in that situation. Okay? And that's it. I mean, that's really what's going on. I mean, not, like I said the other day, we haven't really gotten any calculus, right? That'll start on Friday, but this is the pre-calc stuff and the stuff with functions and our calculators that we need to be able to do as we go forward. Okay, so, yes? Most quizzes are about 30 points, right in that ballpark. So I assume that's, give or take 3 or 4. Okay, so, quizzes are typically going to be, the majority of our grade, probably 75% of grade. I don't know, I never really percented it out. We have a daily grade when I come around and take a look at stuff. I'll put in every week or two, I'll put in a 10 or 15 point grade. And then we have a few other things here and there, and of course the term, but most of it's our quiz grades. Yeah.
What about any questions?
I don't know, I haven't really kind of, I just put it together. I had somebody take it ahead of time, but it's a front back. I don't know, 8 questions maybe. Most of the time I give you most of the block. I mean, we'll probably start fairly early in the period. I mean, I suppose if you have a few questions at the beginning, I don't anticipate there'll be that much, but we don't take a whole lot of time. I'm fairly vague, and especially third block. Third block always seems to come in with a few more specific questions about the quiz than second block. It's fun. I mean, over the years, third block always seems to come in with kind of a, oh, hey, what about? Almost as if they knew what was on the quiz. So, you know what I mean? I always tell second block, I say, why do you do that? Why do you help? Why do you tell me? Switch, yeah, I know. Maybe if you guys the quiz on Monday, and then give them the quiz on Tuesday or something. So then you get the opportunity. No, you guys, that wouldn't help you. But didn't seem to help the grades, so I'm not sure. So anyway, the other class had a lot of questions about what's the average, it's hard to tell. This quiz, I was saying the other day that there are always going to be a few questions probably on there that might not seem like the homework questions or exactly like the homework questions were, but they're about the same concept, but it's the idea of, can you take this concept, do you understand this concept well enough to apply it in a new type of problem or a different type of situation? So it's certainly about the concepts we've been learning, but it's not going to be just examples of the homework problems with different numbers in it. You know what I mean? I mean, there's going to be a different twist probably to a few of the questions. That's just the level that we should be at. We should be able to do that. But there will also be some that should be, hey, if you've been doing the homework and you've been paying attention to class, I mean, this should be just like we've been doing. But there'll be some others that make it stretch a little bit. And it's kind of that way on. And can't really study for those. What you do is you just keep up every day. You ask questions as you don't understand something, and you just try to stay on top of things. I mean, that's how you do that. Yeah.
How similar would you say that questions on these quizzes are to, say, how
That's a good question. Very similar. I mean, very similar. I don't know. Different Calc 1 courses in college are just as different as the professors. There's many different professors. Some are very old school. It depends on the text they're using. Ours is a very kind of newfangled, reformed kind of. I know the books don't look new, but reform-oriented kind of calculus. A little different than the traditional drill and practice kind of calculus. So, I think it's very similar. Yeah. You know, I gotta admit, and I'm maybe kind of a nerd, but the math, you know, one of the things I like about this book, these authors do have, well, you can decide if it's a good or bad sense of humor, but they have a sense of humor. And the reading, it's about as readable of a calculus book as I've ever seen, okay? It is very readable, and they do a pretty good job. If you do look through their examples, and you do look through the reading of some of these things, they really do a pretty good job. And I really like their problems. Their problems don't look a lot like a lot of traditional calculus textbooks, but I really think that once you get used to it, and as we go through the year, it really helps your understanding. You haven't just memorized a bunch of, you know, do this, do this, do this kind of stuff. Sure, there's some memorization that comes along with it, but I really think the way they ask their questions and the way you have to do those kind of questions on a daily basis really helps you to understand the concepts that are in calculus. I think our AP test scores have been fairly indicative of that it does do that. So anyway, you know, there might be a little bit of getting used to those type of questions, whether it's on the homework or on the quizzes as we go through the year, but you know, do the best you can and adjust from there. You know, some people, every year after the first quiz, some people don't do very well. And what can I do? Well, you know what? Do something different maybe. You know, if you haven't been coming in to get help, if you haven't been asking as many questions, if you haven't been doing the homework, whatever, then change something, right? What's that saying? The definition of insanity is doing the same thing over and over and expecting different results, right? So, you know, but anyway, we'll see how it goes. I mean, for the most part, I think you've been doing what you need to do up to this point. But I do have a few zeros in the grade book I mean, not in the grade book, but on my homework sheet. So, you know, there's a few people can pick up the pace on homework a little bit, but for the most part, people are doing well. All right, let's do this next. Let's talk about some trig stuff and then give you some chance to work on some of that, review for the quiz. Mr. Cool?
Miss Clark.
Mrs. Clark. Okay, so I feel bad for those of you with Mrs. Clark. You'll be at a little disadvantage, but we'll see, make it work. Now, I think though, I think I did talk. You can blame me for this. I did talk her into making you memorize the unit circle.
Thank
Right.
you.
Okay.
Would you let me know? I don't know.
You still don't know it? Okay, I don't remember it now. But the, and I know Mrs. Payne has made you do that. Now, so we're gonna talk about if you have memorized unit circle, not memorized unit circle, and what that means, and what you may have to do to adjust for that. But, so let's go through some of this. Now, on tomorrow's quiz, you know, any trig, if there's a trig graph or something, you'll have your calculator to be able to graph it and set the window and all that stuff. So you don't have to worry about this. But going forward, you know, I don't know when it'll be, whether it's the next quiz or the next quiz after that. You know, for sure, probably in the chapter 2, one of the quizzes in chapter 2, you'll have to be able to do some trig stuff without a calculator. Okay, so that's what I want to kind of review now. Now, after we go through this and after we do some of this homework, if you want to come in and get a little extra trig practice, then please come in and do that. That'll be just fun. Okay? So the first thing I wanted to go over here is that if we just look at an angle, and we work in radian measure all the time, okay? So if I just have this angle go, oh, I know. No. I got too many windows open. And I'm recording, the screen recording, that takes up some All right, that should work a little better. Okay, so first of all, what is this whole business about radian measure? Well, if we go here in degrees, if I go up here to about 30 degrees, let's say, okay? Now, radian measure is the length of this arc on the unit circle. Now, why is that, or what does that mean? Well, if we look at the unit circle means we have a radius of 1, okay? Okay, the unit circle means we have a radius of 1. Oh,
Whoa, that is weird. Oh
all right. So the unit circle means we have a radius of 1. And so what's the circumference of a circle? What's the
my.
equation?
360.
No. I love the enthusiasm. Right or wrong, doesn't matter. Just go for it.
2 pi r.
2 pi r. There we go.
Pi.
2 pi,
Pi d.
or pi times diameter. Now, if you're talking about a radius of 1, what's the circumference?
2 pi.
2 pi. So on the unit circle, the distance around the unit circle is 2 pi. That's why we say that 2 pi is equal to 360, or pi is equal to 180. Okay? It comes from circumference. It comes from, and didn't you do a project with string and,
Oh, yeah.
right, drawing? So that's the circumference around, and so that's what radian measure is not the rotation, which is what degrees is. The rotation of that rotation on the unit circle. Because if the circle has a different radius other than 1, then of course degrees is equivalent to pi. We say that would be pi 6, right? Pi 6 is 30 degrees. But also pi, remember, pi is just a number, 3.14159 divided by 6. That's roughly 1/2. That's roughly 3/6, roughly 1/2. So when we say that all the way around the unit circle is 2 pi, we're really saying all the way around is 6.28 units, radians. Okay? So right here we went about half a radian. Pi 6. Pi 6 is about 3/6. Okay, so radians, even though we usually talk about radians in terms of pi, the only reason we talk about it in terms of pi is because the circumference of a circle is 2 pi. But we could just talk about them as decimal numbers, okay? So here we go. We keep going. And we got come on. Oh, oops. No. There it goes. Sort of.
There you go.
Yeah, every time I clicked, it was building up. All right, so when we get to 90 degrees, that's pi halves. Well, pi halves, that's about 3 divided by 2. That's about 1.5. Okay, so when it gets up here, it's at about 1.5 radians. Okay? And then when it gets over here, pi, that should be about 3.14 and so forth. Okay? So that's this whole business about radians. Now, another thing we can do with sine and cosine, and you remember this from geometry, this is just SOHCAHTOA, right? Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent's opposite over adjacent. That can come in handy if you haven't memorized the unit circle, and we have to do reference angles and triangles, and you have to remember your 30-60 and your 45-45 triangles, which might be something some of you will do. Okay, now here's the unit circle. Okay, now if you had went on here and memorized these values, okay, you probably memorized something like this. You probably memorized that at pi 6, which is where we're at right now, that you have these two values. Now you might have memorized it this way. Let me find, hopefully we're not too bogged
Okay, bear with me a minute here. Okay, why is all these things with me? Hang on here a second. Well, this was looking pretty slick for a while ago. Okay, thank you for your patience. Okay. Well, there. You just feel this thing kind of screeching to. Yeah. Yeah, this will. Here it comes. No, it's all right. And there it is. All right. So now what you have here is, you remember which one of these is sine and which one is cosine? Which one is which? Cosine is first, sine is second. Now, the reason for that is because of the SOHCAHTOA thing. If right here you'd have opposite over hypotenuse for sine. Opposite over hypotenuse, that'd be 1/2 over 1. So it's the y value. And cosine is adjacent, which would be this leg over 1. So cosine is the x and sine is the y. And so if you remember those values, okay? So sine of 30 degrees or pi 6 is 1/2. Cosine is square root of 3 over 2. Okay? Now, if you haven't remembered those, or you haven't memorized those values in the different quadrants, and even if you have, this can be helpful if you're having trouble remembering them for sure. This can be a good kind of a double check. Is we can say, all right, you know, and let's just review this real quick. Pi 6 is a value that would come up a lot. Pi 4ths would be a value that comes up a lot. Pi 3rds. But also pi halves and pi and 3 pi halves and 2 pi. Those would be the values you'd be on the lookout for. Okay, for radians. And then these would be the values you would also be on the lookout for. What's another one? Root 2 over 2. 0, 1, root 3 if you get into tangent. You could have root 3 over 3 if you get into, also into tangent, I think. Okay? So we want to look for, be thinking about some of those values. Now, and these would be the ones we'd kind of be on the lookout for. Now, if I had to do, if somebody asked me to find the cosine of 7 pi 6, right? And this would be something we might have, we need to be able to do without a calculator. So what would be your thought process on finding that? Find out which quadrant it is. Some of you like to change that into degrees. So you could go 180 over 6, that's 30, times 7, it'd be 210 degrees. I personally just stick with radians. Turn those into fractions. Think of that as 6 pi 6. Right? Isn't that pi, 6 pi 6? Or if you're working in thirds, it'd be 3 pi thirds. Or if you're in fourths, it would be 4 pi fourths, right? So think about that as 6 pi 6. So what do we need to go? We need to go one more to get the 7. So we would be down here, and this would be a pi 6 reference angle right here. Correct? Now, what do you know about pi 6? Well, if you memorize the unit circle like Mrs. Payne, maybe Mrs. Clark had you do, wouldn't this be a 1/2 here? This would be a 1 here, and this would be a root 3 over 2. They'd be negative, because here you went left and here you went down. Now, Some of you might not have memorized it that way though. You may have memorized it this way just based on a regular old 30-60 triangle. And this and it goes back to geometry. 1, root 3, 2. Anybody memorize triangles that way? Remember that from geometry? And if you already know the unit circle, fine, and maybe I'm wasting my time doing this. But if you don't know the unit circle, I know there are some people who just do it this way. And if I had a 45-45, you know, just it's a 1 and a 1 and a root 2. Okay, but the way I know the way several of the other teachers did it is they put a 1 there, they put a 1/2 there, and they put a root 3/2 there, across from the 60. And on this one it'd be what? Root 2/2, root 2/2, and then 1. That way we always have 1 on the hypotenuse like you have on the unit circle. So if you've memorized them either one of those two ways, that's fine. Okay? So now we come back to this. So either way you did it doesn't really matter. If you're putting a negative root 3 here and you're putting a negative 1 here and you're putting a 2 here, you can do that. And then you do SOHCAHTOA. So if I wanted to do cosine, it'd be adjacent, negative root 3 over the hypotenuse. So it'd be negative root 3/2. Right? If you're doing it, you know, the other way, it would just be the x value. Whatever the x value is your cosine. Whatever the y value is your sine. So it'd be negative root 3/2. So either way, that's what you get. So we need to be able to do that. All right? And then we also need to be able to go the other direction with that. We need to be able to do this. We need to be able to answer this question. Where does sine x equal negative root 2/2? Where does sine x equal negative root 2/2? And we'll just look from 0 to 2 pi. Okay? Well, maybe you've got that just memorized. It wouldn't be thirds, I don't think. It's got to be pi fourths. Now, how do you do this? Well, first you ask yourself, where is sine negative? Now, I don't know if you do the AS, this whole thing, right? If you like that, CAS thing. All students take calculus. There we go. Sine and all of them are positive up here, so sine is going to be negative down here. So we're going to be in the third and fourth quadrants, right? That's where sine is negative. Now, if you remember that sine is the y and cosine is the x, well, then you're asking where is sine negative is like asking where is y negative. Well, it's down in the third and fourth quadrants where y is negative. So we're going to have triangles in both of these two quadrants. Now, sine is the y, so this is going to be negative root 2/2, negative root 2/2. And isn't that a 45-45? Right? Root 2/2. And so this would be negative root 2/2. And then this is 1. Oh, that'd be positive. Thank you. And of course, hypotenuse is always positive. Okay? Or if you did it the way I was talking about, now maybe Mr. Cool doesn't do that. Maybe nobody does it that way. It'd be this, this, and this. So, where are we at? Well, you say that's a 45-45, which makes that a pi fourths reference angle, right? Well, what is this? This is pi. Pi, of course, is 4 pi fourths. This is 2 pi. Well, that's 8 pi fourths, correct? Pi and 2 pi. So what do we got here? We got 4 pi fourths plus another pi fourths. So that's 5 pi fourths. And what's this one? Yeah, this one is 1 short of 8 pi fourths, which would be 7 pi fourths. And so there is the answer to that. So again, each of those are important problems to be able to do. And they have to do with these important kind of things here. Now, the other piece is, what about ones that don't make triangles? What if I ask you for sine of pi halves? Well, you got two choices here. One is the unit circle option. Where's pi halves? Right here. What's the y value, since we're doing sine, of that point? The y value is 1. So sine of pi halves would be 1. Okay? Now, the other way you could get that is to just draw yourself a quick sine curve, because you should know the sine curve. here's pi halves, here's pi, here's 3 pi halves, here's 2 pi, right? So what's sine of pi halves? It's this output right here. It's 1. So if you like the unit circle, do it that way. If you'd rather do a quick sine graph, sine of pi halves is 1. That's an easy way to get it also. Okay? And then likewise, if I ask you where does cosine x equal -1, well, the unit circle way of doing that is saying cosine, okay, cosine is the x-coordinate. Where's the x-coordinate -1? It would be back here, right? Where's that at? That's at pi. Another way to do it is to draw the cosine graph and say where does cosine have an output of -1? It'd be right down here, which is where? At pi, because there's pi halves, there's pi, there's 3 pi halves, there's 2 pi. So, right, so you can either do, so these 1, -1, 0, these pi half, pi, 3 pi halves, the ones that are right on the quadrant, you can do with the unit circle or you can do with the little quick sine cosine. Okay, one last thing I want to show you that's kind of cool. You got to go to that. Yeah, just sit that there. Okay, so I just want to show you this, and you might have seen this in trig class last year. If we're going to look at the sine graph and compare it to the unit circle, just watch this. Okay? Now, as that point goes around, let's think about the two things we're looking at here. The red is the arc. That's the radian. Okay, well, that's what we have down here on our x-axis, is radians. Pi, 2 pi, so forth. So this red length is the same as that arc length, because that's what radians are. Sine is the y value on the unit circle. So we're plotting that right here. And so this blue length should be the same as that blue length. Well, watch what happens as you go around the unit circle. You remember seeing this last year? Okay, and so see how the sine, the y value is getting less? So right down here, the y value is 0 on the unit circle, and look at the graph. And now the y value goes negative, so the sine graph goes below the x-axis. And now the sine graph is negative, but coming back towards 0. And so that's why one cycle of the sine graph looks the way it does. Okay, so you can compare the unit circle to the sine graph there. And then if we look at cosine and do the same thing, okay, cosine, of course, is the x. And the radian is still the red. And so the x-coordinate actually gets less as we start going around the circle. And now the x is actually negative here and getting more negative, so you can see the cosine graph go. And now the x is still negative, but getting less negative, so you can see the cosine graph over there. And then finally the again. Okay, let's do one example problem together. And then I'll give you a little bit of time. All right, so this is something that'll be, well, what the heck, since it's Halloween, we'll just do one. Great Halloween gift. There you go. Yeah, isn't that nice? I'm so proud. Yeah, it is. Yeah. Now, there's some in the book too. I know.
Happy Halloween.
Happy. Here's your home. All right. So let's do number. Let's do number 2. Number 1 is too easy. All right. So, all right, let's take a look here at problem number 2 on the worksheet. Now it says sine cubed x, right? What else does it say then? Minus 4 sine x equals 0. So this is what we're going to have to do. We'll have some calculus problem. We'll be looking for some calculus stuff about this function, and we're going to have to solve this equation to move forward in the problem. So we're going to have to solve this. It's a no calculator problem. Okay, so tell me the algebra I would do to this first. Factor out a sine x. Okay? Sorry. I did something weird. You might need to. You can do it on the back if you want. Now again, I am not going to come around and check this tomorrow, so you know you'll have a little bit more of an assignment tomorrow after the quiz. But if you want to focus on this more here in class and then the next day, fine. But let's factor out a sine x, and that leaves us with what? Sine squared x minus 4 equals 0. Okay, so what's that mean? No, we don't want to divide. What we want to do is we want to set each one of those equal to 0. Right? If these two things multiplied make 0, then either sine is 0 or sine squared x minus 4 equals 0. Okay? Now what could we do with sine squared x minus 4? We could either factor it out or add the 4. Let's add the 4. It doesn't really matter which one we do. Square root both sides as long as we remember that it's plus and minus. So now I've got sine x is either equal to 0 or sine x is either equal to plus or minus 2. So let's do sine x equals 0 first. Where does sine equal 0? We think of the unit circle. So it would be where the y is 0, which would be at, wouldn't it be at pi also? So it'd be at 0. Now how do we write this? 0, it'd be at pi, it'd be at 2 pi, but then wouldn't it be at 3 pi, and then at 4 pi, and wouldn't it just go forever and ever? Remember the pi n thing? So this would be 0 plus, yeah, we wouldn't even do 2 pi n probably because it's every pi it repeats. So, and of course you wouldn't even need the 0, and n is a 1 or a 2 or 3 or a negative 1, right? You could go backwards. It could be negative pi or negative 2 pi. Okay? Now, if the problem would have said from 0, because I think some of your problems do, some of your problems say from 0 to 2 pi, but don't include the 2 pi, we would have just stopped with 0 and pi. But I think on this one, number 2, it says for all x. So we want to have this. But now over here, when does sine x equal 2? Here's the sine graph. Sine graph never equals 2, or negative 2. So there's no solution to that piece. So it's just this right here. That's the whole solution right there. So sometimes you don't have to draw the triangles like we did on the last question. Okay, sometimes you have to draw the, sometimes we have to draw the triangles when we get to this point to figure them out. And sometimes the unit circle or whatever. Okay, so that's it. Yeah. Yeah, technically, I'm not going to be that picky about it. Yeah, technically you would say 0 plus pi n, and n is a member of the integer, an element of the integer. Okay. We'll just assume that. Okay. Now, your other part of your homework is Appendix F. Now, I'm going to change it from your assignment sheet, though. I'm going to shorten it a little bit. Okay. Happy Halloween. Appendix F. 17 through 34. Oh, 17 through 34, Appendix F. And most of those are just, the first couple, you have to think a little more. But then after that, it's mostly what's cosine of pi 6, what's sine of 2 pi thirds, what's, just quizzing you a little bit on those memorized ones. Okay?
We do.
I don't think we probably do. No. 17 through 34 in Appendix F. 17 through 34.